As already mentioned, my name is Bartosz Sypytkowski. If you want to reach out to me anyway, after the talk in the upcoming days, here are my handles. And what we'll be talking about today? We'll be talking about distributed systems, eventual consistency, and how to manage and synchronize the state in this distributed system manner without need of basically any living synchronization primitives. I mean, situation when we prefer high availability over the strong consistency, because this is what is so exciting about distributed systems, right? That we can be available even in the phase when some of the machines are, coming and going out of our clusters and so on. And we'll be focusing solely on the CRT, so conflict-free replicated data types. And we'll talk about what scenarios could we use them for, how to build them, because it's not always that easy to just use the framework or database. You need to understand the underlying fundamentals in order to avoid some rather worrisome bugs in the future, right? We'll also talk a little bit about different notions of time, because this also concerns distributed systems as well. So without further ado, let's take some, let's say, real-life case study to begin with. We'll try to build a YouTube 2.0. Well, maybe not the whole YouTube. We'll cover the few scenarios that are interesting from our point of view. Well, first of them is traditional video streaming. As in any globally replicated video streaming platform, we can imagine that when, for example, Alice wants to share their video on our YouTube site, right? She first needs to upload it on some kind of data center. Later on, people from all over the world are able to see that video. However, if this video becomes popular, it might be this single server containing the video can be a bottleneck. Also, in case if that server went down, we'll no longer be able to see that video, right? So what do? We replicate, we copy that video onto different servers, possibly living in the different data centers. This not only allows us to achieve better availability, but also less latencies and stuff like that. And this is simple because there was a single person uploading a single instance of the video, right? I mean, we can have multiple uploaders, but any one of them is there is only one person at the time altering the content of that video, right? It's Alice. However, let's add another feature. Let's say that we want to present a video view counter on the same site. Now, the things start to differ a little bit, because the counter is also a single entity, the counter per video, right? However, the issue is that it's updated from multiple places all over the world, all at the same time. So what do? We need to be able to update the same logical entity, replicate it on the different servers at the same time without reaching into invalid states, like what is the correct value of that view counter? We need to be able to answer that question, and there are two common ways to do that. One of them is based on the consensus protocol, and this is how many of the distributed systems works right now. For example, Kafka, any kind of distributed SQL databases are all based on consensus protocols to do so. You can know them from names like Paxos or Raft. Different names, different protocols, but the general idea is more or less the same. So let's say that we have one server that is responsible for coordinating the update of our site. And we have usually an odd number of servers in general. I will mention why in the second. And let's say that we want to change the value of that view counter, right? So this proposer sends an update request to all of the acceptor, all other servers that are supposed to update that value. This is part of something we called two-phase commit. So first we are sending the request to all of the acceptors, and then wait for the majority of them to respond before we continue to the next phase. Why majority? Because if you think that at the same time another proposer could send an update request, we could run into a situation when we end up in conflicting states, right? Because if we didn't get majority of the acknowledgements from our acceptors, then it could turn out that the same value could have two different values to the same, let's say, register or key value pair could have two different values, because one proposer got half of the acceptors, another proposer got another half. This is why we wait for the majority of acceptors to answer. And then once this is done, we are ready to send a commit message, which will say for all of the acceptors, okay, you received that update, now you can commit it, and this will be a new value of our view counter entry in the database, right? And then we are also getting an acknowledgement in order to be sure that everything went smooth. Now you can see that this takes 2 round trips to establish a single increment of view counter for our video. Is this a problem? On a single server, it kind of still is, but when we are talking about planet scale replication, it takes a much longer time that we initially thought about. For example, if we take a round trip time between data center in Tokyo and London, it takes almost 300 milliseconds for a single round trip time. For this kind of protocol, we need 2 round trips at least. So the problem here is that given almost 600 milliseconds time window necessary for updates, we can only have a few view counter updates per second, right? Very few. If we want to get into something like YouTube scale, this won't help us, right? Because nobody will want to watch the video if he had to wait several minutes in order for his or her view counter to update for that video, right? This would change dramatically into our disfavor. So there is another way to do that, because maybe, just maybe, we don't need to know exactly what is the view counter value at any given time. Maybe we can know that eventually when all of the people will stop viewing that video, and after some time we'll get all of the updates that are pending in the process and eventually get the correct value. But at any given point in time, we just prefer high availability of our video rather than having exact precise number. So this is not the only use case. There are several different. In general, we could say that this is a common scenario anywhere where network latencies are high. So planet scale replication is one of the common examples of that. In future, when we'll be traveling to the stars and maybe have databases spanning over entire planets and between planets as well, then this will also be even bigger problem. Another thing is a situation when we have devices like mobile applications, which should be available to get incoming updates even in a situation when they are periodically disconnected, because in this context, we could think about disconnected device as a device with a huge lag, basically, very huge latency. It's pretty much the same idea. Another thing is navigation. So when we have a huge amount of updates coming from a huge amount of devices, chat applications, collaborative text editing, so something like Google Docs, or maybe even Google Docs that doesn't need any server to synchronize, something that works only on the computers connected with each other via Bluetooth, for example. Any kind of mobile advertising, and this was actual case for CRTs in I think it was in Rovio, the creators of Angry Birds. They've used CRT counters for their mobile advertisement platform to count the number of impressions, so number of times their users view given advertisement. And any sort of edge computing. So when we want to perform computation on the client devices rather in some servers living in the data center. So the question here is, can we synchronize data safely without the need for consensus, right? Can we somehow avoid making this consensus, protocol in favor of having higher availability with lower latencies? And it turns out that, of course, we can do. There are even existing databases that are propagating this approach. Some of you might be familiar with React, which I think is the most known database having those capabilities at the moment. Amazon DynamoDB is also capable of that. Azure Cosmos DB, in general, it's not capable of doing those kind of computations, but it provides a special kind of synchronization option, which is called multi-master, where we can basically write down our own something like stored procedures that are responsible for handling conflicts between updates happening on the different servers. So this is exactly the case when we would like to build our own CRTs, because if we can build something like CRT in JavaScript, and we can, on top of some stored procedure that will be automatically working inside the Cosmos DB, then we've created our own CRT database, basically. There are many others. I was also involved in a few of those, and this is the reason why I'm speaking here, basically. So yeah, I can say that DTLife is the project I was working in for the last few months. And it basically allows you to build a JSON-like document database on top of mobile devices. And it's SDK originally written in Rust with the clients in various different languages, basically anything that modern mobile platforms are supporting. So we'll cover a subset of CRTs. Of course, this is a very wide topic. We won't be able to talk about everything. So we'll focus on something that we know as state-based CRTs, something that works on React, basically. And we'll cover how they are built and what the trade-offs are they propagating and how do they work. So we could build our own, for example, on this Azure Cosmos DB database, right? So the general principle is that we could avoid consensus, so avoiding conflicts, I would say, if we could resolve those conflicts every single time whenever those are made. And we can do that if we provide enough metadata for our servers to get to the same conclusion every single time. So how does it work, more or less? Let's say we have two servers with two different, with the same entry, the same logical entry, having two different states, right? Because it was updated on one replica, but the update was not yet propagated to another one. So basically what we need is to serialize that state or part of that state, replicate it over the network, broadcast to all other replicas, and do something that in state-based CRTs we call merge operation. So merge operation is a method that is responsible for resolving all possible conflicts that have happened between our CRTs, between two different versions of our CRT data type. And as it turns out that in order to do so for state-based CRTs, all that we need to do is to be able to establish convergence. And what is convergence? Well, it's an operation that has three different properties. First, it's commutative. It's useful because if we manage to do so, the order in which we apply the operation doesn't matter. So we could build updates on different replica sets that we have, different versions of the same logical entry, without need to synchronize. This is the basic rule that we need. Another thing is that they have to be associative. So again, order of operation doesn't matter, but with extra steps. And last one is idempotency, which means that if we apply the same update twice, the result will be still the same. This is also useful from a network point of view, because this means that we can send the same update multiple times over the network and don't worry about changing the result of our system, right? Well, so now let's stop and think about the most basic primitives that we have, let's say in mathematics, that achieve those properties, because those are mathematical properties, right? Well, let's start from number addition, right? Is number addition convergent? And the answer is no, because, well, while it's commutative and associative, it's not idempotent. If we add 1 plus 1, we don't have 1 in the result. So what are some basic operations that are maintaining those three properties? Well, one of them is maximum or minimum value of two numbers. Another one is union of two sets. And as soon you will see, we can do many different things based only on those two very simple rules. And when we are talking about sets, we quite often mean also maps, because if we have, for example, a dictionary of values, the keys in the dictionary form a set, right? The values not, but if we will be able to establish the merge operation for the values, and we know that the keys already form a set data structure, then we can combine those together to build something that will maintain our properties. So let's start from building this distributed view counter. This is the example C# code here. So basically what we have here, I will come back to this later. What we have here is a very simple map, very simple dictionary, where each of the replicas has its own entry. And the key here is that when we want to increase the counter value on each replica, this replica takes the corresponding entry on its own side. So let's say we have replica with identifier A, we'll take that entry and we can increment it. This works for grow-only counter, in short, the G counter, where the values can only grow up. If you want to have the total value of that counter, we just sum all of the values that replicas have, incremented over the time. It's simple, right? Now, how do we merge that thing? Well, it turns out that since this counter can only grow up, because this is where the name comes from, right? Grow only counter. So basically, we know that if we have two different values for the same entry, the value that is higher than the other one is the more up to date, because this counter can only grow up, right? So we can simply create a merge operation that will take all of the entries from different replicas pairwise and take maximum of their values. And this will be our merge operation. It's that simple. Well, growing only upwards is kind of limiting, let's say. We sometimes would like to be able to increment or decrement the value, right? So example of that could be something like distributed like counter. So we want to hit like on something and have a like counter increment, but we also want to be able to unlike it at any given time. So to revert that operation, we need to be able to decrement that counter value. And this is where the composition comes to. And we could think about, well, in CRT nomenclature, this is called positive negative counter. And it's very simple. We simply have two G counters, and the value of our G counters is basically a value of incrementing G counter and value of decrementing G counter. So whenever we want to increment the value of our counter, we add that value to the increments G counter, and whenever we want to decrement it, we again revert it and increment the value of decrements. And our final value is just a subtraction between the two. Merge is also pretty easy because all we need to do is to merge those. This is where the composition of those data types comes to, and it gives us some nice and very powerful possibilities that we later can use to build our own data types that don't exist in React, in basically any kind of database that we already seen in the one of the slides before. So once we have this in our belt, let's think about something more difficult. Let's say that we want to have build a list of followers, like on the Twitter, right? We can follow a person and unfollow him or her. And in this case, we want to be able to create that, let's say, set of followers in distributed manner without need of consensus, because we really don't care if we know exact number of those followers at any given point in time, right? We are just fine if we eventually hit the correct value, the correct list of them over time, as you know, the replica will manage to synchronize between each other, sending the updates to each other. And as we already mentioned, sets already satisfy those convergence properties. So there is something called the gset, grow only set, just like gcounter, which allows us to add values. And in this case, the merge operation between two gsets is just union of those two. Since union of two sets is convergent, then this merge operation will also be convergent. The only problem is that we only can add value there, because if we would remove value from one set and then replicate it to another set when this value was not removed, after the merge it would magically reappear. So this is not something that we would like to see in our system. So the question would be, well, we created a positive negative counter by using two G counters, right? So two counters that can only grow, and we use that to create a counter that can grow and decrement its values in both directions. So can we use the same in sets? Well, there exists such structure, but in case of sets, this is more difficult, basically, because of course we can say that we have set for elements added, set for elements removed, but the problem is that we need to now store removed elements forever. And even more difficult problem, when something was once removed, it cannot be added again, right? Because it again would magically reappear on the other side. So we need a different take. What we really need is, let's say that we will have to see, we need to be able to establish all updates seen by the replicas on another side. In this way, we will say, okay, replica A seen those things, those updates, where updates are additions or removals, so follow unfollow events. And on replica B, some of those events were not seen. Then if we know which of those elements were not seen, which of those operations were not seen, we can apply them on the other side, right? And we'll be there soon, but first we need to go and talk about vector clocks. Well, one of the problems in distributed systems is that we cannot really rely on the time as a wall clock time provided by our machines. You might already have heard that, for example, Google Spanner database is using wall clock time to establish its transaction order, because if we want to talk about updates and operations, we need to be able to set them in particular order. Now the problem is that Google is able to do so by having basically an atomic clock in every one of their data centers. We are not able to do so, unfortunately. So there are different ways of establishing order in distributed systems, and one of them is about vector clocks. Well, vector clock, it looks rather simple. It looks like our initial gset, but with a little twist. It provides us with the ordering capability, because if we are talking about order of updates, we need to be able to determine which, let's say, timestamp. In this case, our vector clock is the timestamp. Which of them happened before another, right? So this is the question we want to answer. And for vector clocks, it's pretty simple. We just compare all of the entries pairwise. So if all of the corresponding entries are equal, we can consider those vector clocks equal. If at least one of them on the one side is greater or equal to the entries on the another side, you can say that this vector clock is greater. So let's say it has more fresh data than the other one. In reverse direction, you can say that they are less than. When one vector clock is lesser than other, but as you can see, there is another possibility. So what happens when some of the entries are greater, some of them are lesser? It means basically that those two vector clocks are concurrent to one another. What does it mean? It means that two replicas created an update operation on their sides without having the synchronization from another side. So let's say that on one replica we added Ben, and on another replica we added Emmy. And in this case, those two replicas will have concurrent vector clocks, because replica B, for example, didn't receive the update from replica A before it made its own update. So this is some of the ordering capabilities that we could take to our advantage as well. If we are able to say that two operations happen concurrently, then we can decide what should happen next. And yeah, here is the code, C# code that basically does that comparison, but I guess you will be able to see it later on, so we don't go into details here. And another thing, since we were already talking about timestamps, right? Well, let's say that using an entire vector clock to timestamp every single operation is kinda expensive, right? However, we could use something that is much more lightweight, let's say, because basically what we need here is ability to say, okay, we need to timestamp that add or remove operation, right? And we can do so by giving it some kind of unique ID. We, again, cannot use timestamp based on the wall clock time, especially that we cannot provide that 100% of the time two different servers won't assign the same timestamp to any given value. But what can we do? Well, we know that, for example, for databases, we provide unique column ID by using sequencers, right? So we assign a monotonically increasing number to every new inserted record. This, again, doesn't work for distributed case because we would need to establish via consensus what the next sequence number should be, right? But each of the replica can establish a sequence number on its own. So if we combine that with this replica identifier, we have something that's called dot. Dot is the unique identifier of any given event in distributed system, basically. Now, as you can see, if we imagine this space as, not a timeline, but a discrete grid of events that could happen and be marked with those dots, we'll see that with the updates happening over time, this blue area on the left of that diagram will be slowly filling as long as we are sending replicated replicas of the data types that we are updating over one replica to another. So we can see here how more or less the observation space of our update should look like. This is something like, in database we say, okay, this is the state of the record at the date, for example, 1st of July 2019 at this hour, right? And this is the timestamp that is defining this, the state of the record at that time in our SQL database, for example. And this diagram, this grid, is exactly the same for the distributed system. So we see, and we can tell that the record that we have that is marked with this data structure says that this data structure is up to date to all of the events that happened up to the, for example, D4, C5, B7, A5, and there are some updates on the right, we call them .cloud, that happened out of order. This can happen if our network protocol will deliver messages out of order. If that doesn't happen, this should never even appear. This should never even happen. Now, given that observation that this area on the left has no holes in it, so it's a continuous space, and it's usually in reality it's the biggest part of our collection, our database, our data type. We can describe it basically as this vector clock we talked before. So this area on the left is basically a vector clock which describes only the edges of particular replicas, and the dot cloud on the right is basically a set of dots that are remaining. And as our replication progresses, those dots will be glued together into this vector clock. Now we can create our set of followers into something that we call add wins observed remove sets. I know this is the long name, but well, CRT were created initially in academia, so I guess they are not very good at naming. But now, we've said that the thing on the right is basically a timestamp describing the current observed state of the world for the data type that we can see on the left. So we basically have a set of followers, Alice, Ben, Dylan, and Jane, and every one of them has a dot that is describing when this event has been inserted into our follower structure. Now, let's see how this could look like. So yeah, this is our set. This dotted version, vector version, is the thing on the right, and our dictionary of keys with hash set, because multiple people can, in theory, add the same element at the same time before the replication happens. Now, let's say that we want to add another follower, Emmy, at replica A. What we need to do? Well, we first take a look into the vector clock at replica A, increment it. This will create a new dot, A3, and we use this dot to mark Emmy as a new entry in our active set. And that's all. We can present it just like that, using this code. Now, removing element is even simpler. For example, we say we want to remove Ben, so unfollow operation on replica B. All we need to do is to remove it from the active set, and this will work. And why, we'll talk in a second. Now, the merge operation might feel kind of hard in this context, simply because we marked, of course, we marked the addition with the timestamp with this dot A3, but when we wanted to remove Ben on replica B, we didn't do anything basically. So how does it work? Well, it's pretty simple if you think about it for a little. One thing, if we have removed element, we can notice that, for example, we are comparing replica A and replica B states, right? And we see that Ben is not present on replica B in their active set. However, the dot that was used to add this entry, A2, is seen on the observed set of those in this vector clock we have on the right? So what does it mean? It means that, okay, I know that this replica B, it's seen that I've added this update, right? That I've added Ben because it has the necessary dot that was generated by me. But I don't see Ben inside the active set of that replica. What does it mean? Well, the only possible answer is that somebody had to remove it. So I will remove it from my set as well. And when it comes to Emmy, I've seen that Emmy as well. Emmy is not there. It's not on the replica B side because it was added on replica A. However, Emmy was marked with .A3. And when I see the replica B vector clock, I don't see A3 there. I see that it has only events up to A2. So that means that this insertion update, this insertion operation was not seen on the replica B. So all I need to do is basically insert that element there. So we can remove Ben from replica A and add Emi on the replica B. And eventually also increment also merge those two vector clocks together, just like we merged G counters, sorry. So we are taking maximum value of A2 and A3, which means that A3 is most up-to-date value of that observed counter. And this is basically it. After our merge operation, those two are merged together. And this can be presented using this kind of code. This is only the example. And again, this way we created something that can work on different servers spanned over the entire continent in consistent way. Those are mathematical properties. We know that they will work every time in basically less than 100 lines of code. And I think this is awesome. You can write this code also in JavaScript if you want and put on Azure Cosmos DB. You can write something like that on your servers and, for example, put it into Redis. However, Redis also has an enterprise edition which offers support for those seeded data structures onto its own primitives. So you can do this kind of operation on Redis sets, Redis counters, and so on in the manner that we've just described here. But it's most important that you can build that alone by yourself, even on plain SQL base. Now, the issue with from one side to another was that, for example, let's consider that somebody has followed Elon Musk. Elon Musk has around 20 million, I think, somewhere around 20 million followers. One person decided to follow him. So eventually we need to replicate those 20 million followers on all other replicas on all Twitter servers that have this follower list, right? So this is kind of problematic for us. We don't want to spend so much bandwidth and so much money for such simple operation like this. And this is where deltas come into play. So I will describe only deltas based on G-counter, but the same idea comes basically on every single of the data types that we were describing here. So let's say that we have a G-counter. We want to increment its value at counter B by 1. So we basically create a new version, new state of our G-counter, and create some other much smaller state, which is called delta, which also is G-counter. However, this G-counter only contains entries that were changed during those increment operation. So anything that wasn't changed, we just threw off. And instead of sending the entire new state over the network, we can just send that delta that we were interested about, because it contains all of the necessary information that we need to be able to update other replicas on the other machines. So basically, we propagate only the change set, so only the entries that have changed, and this concerns as well values, entries in the new entries in the dictionary, or updated entries in the dictionary that we have, added values on the sets, and so on and so on. This would work the same way, pretty much the same way in the OR set that we were talking about. However, of course, in order to be sure that we didn't miss any update, we need to propagate and be sure to receive and merge all of the changes, because if we would miss at least a single event over the course of time, then we could have potentially out of date state for the entire life cycle of our system. For that reason, of course, you can build some network protocol that will guarantee that those updates are sent and received on the other side. Since this is idempotent data structure, you can basically send those updates every 10 seconds. I know this is crazy for production load, but this is the idea that those three powerful properties, right? commutativity, associativity, and idempotency allows us to be very elastic about the requirements of the network protocol that we want to use, which is especially important when we think about mobile devices and things like Bluetooth connection and so on. Of course, we can also send a full state of the replica every now and then, like let's say, every day or something like that. So now, I see that I've gone quite wild with that. The summary. So we've learned about some of the data types that can be used to be replicate over distributed systems in a way that doesn't require, continuous synchronization, all machines being online in order to propagate those updates and so on and so on. We can do that. All of the things that we talked about would work even offline on your mobile device on, any, for example, Evernote program and so on. Now, what's more interesting, you can build entire transactions that way. There is an idea called highly available transactions, and one of those are RAMP, which is, I think, there is no official confirmation about that, but I think that DynamoDB uses RAMP transactions. So if you will be interested about this in the future, then just Google RAMP transactions, and you will get more info about it and how to even implement it. Another thing is that there is a protocol called Cure. One of the database I was presenting was AntidoteDB, which also offers you ACD transactions without I, because those are not isolated, but it didn't matter for the use cases that they were talking about on their side, which also can be used as a globally distributed database. Now, if you are interested about more, there are some links here. Well, my shameless plug is that two of those links refer to my blog, where I'm regularly sending some series of blog posts about CRTs, and also examples of CRTs written in F# if you are interested about it. I was talking a lot about multi-master replication in Azure Cosmos DB. There is official documentation for that, and how you need to write stored procedure for custom conflict resolution strategies. And also Redis Enterprise conflict-free replicated database, which operates in the context of those conflict-free replicated data types, but on top of Redis database, if you are interested as well. And I think I will finish here. I see we have a lot of time left. I cannot hear you, Yuri.
Oh, sorry. Thank you very much, Bartosz. It was very interesting and very useful speak. This is for you. Okay, we have questions in our Telegram chat. I will read them. Guys, please let us know if Bartosz answered on your questions or not, or we need some more questions to answer really your question. Okay, first question. If an operation is not following any three convergence following rules, commutative, associative, idempotency, when one should use consensus-based protocols for distributed transactions?
Well, in practice, as you can see, for example, from the success of Kafka stories, right? Pretty much Kafka is used in every distributed system nowadays. Well, it's not the true, but it's extremely popular, right? And it's still using consensus-based protocols. And often you don't need this global scale replication, right? A lot of distributed systems are just a bunch of servers forming a cluster, but inside a single data center, right? So their latencies are very, very small, and you can basically go very high, very long way using only consensus-based protocols. This is why Kafka is so successful. RabbitMQ also is one of the examples of such approach, even though I think that lately they released something that is called quorum queues, which works exactly in according to the consensus protocol I was talking at the beginning. When you want to have those database, conflict-free replicated data types, is usually when you want to propagate some updates across the different continents, or you are building something on mobile devices that have to be available while offline, and you want to synchronize the state automatically after, going online or something like that.
Evgeny, please let us know if you need some more information. I think the answer was understandable. The second question, and this, how to choose operations. If initial state is 0, for example, the user increased it by 1, and by this we wanted to set 1, not add 1. Then if two users do this, how do we define a resolution algorithm? Whatever we do, we will do it without considering the user's intentions.
Yeah, the intention is a very good word here, because basically CRTs are all about intention preservation. So there is a difference between, just like you mentioned, setting the value of some register or entry, right, and incrementing it by some number. And there is another data structure that I didn't mention about, which is called registers. Basically, the simplest register works that way, that we have a cell for value that we want to store and some kind of a timestamp. This is not waste-free, because in this case, for example, if we have updated the same register from two different places, the one that has higher timestamp wins and its value is stored while the loser value is being removed, right? And this is problematic in many cases when you don't know how to maintain those convergence properties. Because if you cannot guarantee that the state that you want to store is convergent, then you cannot merge it. So you need to choose, let's say, last right wins last. So if it's updated from two different points, we can do only two things. Either decide that the one that is more recent, in our sense, like for example this timestamp, and store it and erase the another, potentially losing data, or store both values, and then whenever a client wants to read the value, it will receive two conflicting values together, right? And it's up to the client to decide what is the proper value of that register. And to take the example, the Git works that way, right? When we have merge conflict in Git, we are getting two values from that merge conflict, and it's up to us to decide which of those lines that are conflicted with one another is correct and which is not. The same rule applies here.
And this is the only one solution for this case, yeah?
Basically, one of the two. One is called multi-value register, so this Git-like concept, and another is last right wins. So the latest timestamp, because we timestamp each of the values, okay. The latest timestamp will win.
Okay. The next question. Do you know or can you recommend any AWR libraries for C#, like AutoMerge for JavaScript? The user thinks that it's complicated to unit test some implementation of AWR set.
Okay, so yeah, there is, well, in .NET there exists an Akka.NET library, but it's kind of huge if you want to have just a data type, right? I'm not sure if there exists any out-of-the-box mature production or radio library written in pure C#. It's usually more like frameworks, libraries, or entire databases that provide those capabilities. On very rare occasion, it's like, just a library that provides only primitive data types. So I'm not sure if I remember anything like auto merge that could be used here on the C# side.
Okay, and does it correct that for production purposes and complicated cases, better to use paid solutions like Cosmos DB or React?
Answer is it depends, of course. So the thing is, you need to answer several questions. How experienced you are with this kind of stuff, right? Because I don't know, if you are working with PhD on that field, then and have simple requirements, like, I don't know, for example, in my job we have the requirement where we have basically a multi-column table, right? And it's every single cell in every single row has multiple cells, and each of those cells can be updated individually, not as a part of one big update, but we basically are merging different states together using this last right-wings conflict resolution strategy. And this is simple enough to write on the SQL table with additional SQL table that holds only the timestamp for each column or each record. And this is enough. We don't need entire infrastructure of React. We don't need, AWS solutions and something like that. We can do this all in Postgres and still have all of the capabilities that Postgres has, because we know how to build it and how to maintain it and how it works. But if you have more advanced requirements, if you need to do some more advanced things, like, for example, those transactions that are working over CRT data types. And one of the reasons why we would like to have them is that those transactions scale basically in a linear fashion to the number of servers. So if you, for example, have one server, you are doing 50,000 transactions per second. If you have two, you are doing 100,000 transactions per second. This is why you would like to have something like that there. But the thing is here that if you are not sure and that you have necessary knowledge, then you probably want to do some on-prem solution, because it's confirmed. You can always look on it on Google or Stack Overflow. You don't need to figure out all of the knowledge here that's necessary all by yourself. However, still, if you are using the databases that are working this way, you still need to understand the trade-offs. Like, for example, add wins, observed remove set, which you mentioned. How does it work in case of conflicts, right? So when, for example, on one side, on one replica, we add the value, and on another side, we remove that value, what will be outcome of our system? So this is still something that you need to understand on your own, because no of the existing solution will solve it for you. Well, they will solve it, but maybe not necessarily in the way that you want them.
Okay, I think this was a very good answer too. Returning to the previous answer and the question, am I right that akka.net contains a lot of data types from the CRDT, which and it is very useful if I want to build a real-time collaborative solution using CRDT?
So yeah, it has multiple different data types. I remember that we have observed remove sets, we have counters, both the growing only and positive negative counters. We have dictionaries that, well, they work more or less like OR sets, but also can take a value if that value is another CRDT type, data type. There are also last right wins dictionaries. So the last updated value in the dictionary will be the one that is automatically stored, which is kind of convenient for most of the time. But for example, what is missing? If you would like to have a collaborative text editor, right? It requires an array, something like array, because sets don't preserve the order of elements. And there is entire section. I didn't mention about this because I had another speak that is covering only the collaborative text editing data types. And those are basically indexed ordered sequence, because this is what we care about when we are writing, several text lines all together, that those letters that we are typing are happening one after another and are not mixed. And this is something that, for example, Akka.NET doesn't provide, at least not yet, but it's possible to add it if, just matter of effort and time.
Okay, thanks. Well, you definitely know it, there is one more approach to build real-time collaboration solutions, operational transformations. What can you tell us about this approach, and what will be your recommendations, which one and when to use?
Okay, so OTs, so operational transformations, work in a little bit different way. However, the problem is that most of the OT solutions that are out there, for example, Google Docs is one of those, right? Apache Wave is another one. I think Etherpad is another one. They are mostly used in the specific context of collaborative text editing, because those update operations made by OTs are very fast. However, the problem is that they usually have limited offline capabilities. So it might happen, for example, that when you are using Google Docs, you will eventually reach into the state when Google Docs will no longer be able to automatically resolve conflicts for you, and will say, sorry, which version of the document are you going to choose? Because we couldn't solve those conflicts. You need to, erase somebody's work, or yourself in this case. And this is the risk with OTs, and this can be mitigated. And the case here is that the more logic you add to the mitigation part of that, by reducing the risk of those conflict resolution algorithm, the more OT data types are starting to look like CRDT data types. So basically, it's like, a gradient between OTs and CRDTs in terms of how conflict resistant conflict resolution resistant, let's say, we want to be at the cost of the performance, because OTs are in general faster than CRTs, but they are harder to prove and to be safe over the longer period of disconnection of or on offline capabilities.
Okay. Well, when we are talking about CRDT structures, is there any overhead of implementing and using a strong eventual consistency? Maybe one needs special expertise and experience. Maybe there are some benchmarks about using such data types. Performance gain, something about this.
Usually we talk about specific implementation, right? Because you cannot measure performance on the pure abstract data structures, right? So I know that AntidoteDB, for example, did their tests, and this is why I've told you that those transactions that they are making are basically linear, because they were making tests for them, and they've reached something like, I think it's 50. Yeah, I think it's something close to 50,000 of transactions, right? Transactions on every single machine. I don't know what was the size of those machines, but it's scaling in linear fashion to the number of machines, without taking in any distance between the machines into account. And I know that React probably has a handful of tests performance for their own, because they had company backing behind it. This company gone bankrupt, but not for the reasons that React was not good database. Basically, React is used, I know that in some betting companies. So when you are doing bets on some, for example, horse races or things like that, some of those companies are using React. British NHS, so National Health Service System, is based entirely on React, and this is one of the greatest success stories of there. And I think that they are having millions of updates. So unless you are having something that is even greater than that, and I think that only systems that are going, faster are basically high-frequency trading systems. Then this might be, the case when you are reaching limits of your React solution. But also, when you are using high-frequency trading systems, you usually have a limited subset of existing solutions available on the market that are very specific for this kind of workloads, like error spike, for example.
Okay, and it is difficult to start CRD, to start using CRDT structures because you need to know a lot of theory. You need to have some expertise, and is it difficult to work with guys who don't know this?
The problem is not that they are very hard, because as you've seen, for example, this G counter thing is it's basically a single dictionary, right? I have implemented in C# in 30 lines of code, so it's not hard. It's just that you need to have some fundamental knowledge to even start it. This is the hard part, because this is not something that you can do. I wrote something, it doesn't work, I will Stack Overflow that thing, right? It doesn't work that way, at least for now. When I've started learning about them, there were even no blog posts on that topic. You had to read directly from academic papers, and this was terrible experience, I would say. And since then, this topic became much more popular. There is a lot of popular literature, like blog posts, articles on the net, on the web, where you can basically go step by step, using even some allegories to real life work, like people exchanging the balls or something like that, and how this works in the context of human interactions, right? So it's much easier to learn, but still, you need to be, at least from my experience, you need to be able to understand at least the core concepts of why things work the way they work, even though they are very simple on their own, right?
Are there any books or only blog posts now about this theme, about strong consistency, eventual consistency? Yeah.
Okay, I'm not familiar about books. There are PhD papers that have hundreds, pages, so it's like a book. But something that I've also forgot to mention, I think that Martin Klepman, one of the very famous guys in that area, posted one day there is an website that is aggregating all of the knowledge people are building about those CRTs in the wild, and it's gathering, basically aggregating all of those links, all of those blog posts in a single place. I can be able to find it if you will reach to me, after the talk, and share it with you, because I don't think that there is, a one book that is something like, 101 of CRTs from start to the end. I mean, there are PhD papers that are basically describing it that way, but if you are not familiar with the Greek alphabet, then you might have some problems with reading that.
Have you ever think about writing your own book about CRDTs?
Yeah, I was thinking about that, but first is that I'm not a PhD person. Second is that writing a book requires you like a year or two of full-time job, effort to write it down. I know, because I know some people that are writing the books. So while I would love to write something like that, I'm not able to do that. I mean, some of the blog posts I wrote have like 12 pages when they are, written into PDF or printed out. So it's like a paragraph in the book if you want to read it.
Okay, I think everyone will go to your blog and will read your blog posts. Well, the next questions, can you tell us some best practices or receipt of architecting an application to use CRDT-based database? I don't know, for example, we need to create stateless applications or maybe something else.
Well, one of the advantages that CRT provides is that you can, for example, use them on the client. So your database is basically distributed on the client devices, which is usually useful for mobile devices. But beside that, there is, this is just a use case scenario, right? There is no inherent requirements on top of, CRTs. Basically, it's more like we have a problem because we are building a database that needs to be highly available, so maybe distributed not only on multiple machines in the single data center, but on the multiple data centers in the case when the entire zone fails. Like, for example, it happened several times already for all of the major providers, and we still want to have that data to be highly available even in the case of such events will occur. So in this case, this is the question. It's not like trying to find if I can squeeze CRT into that place, but we have problem because we are building something. It needs to be highly available. It needs to give us low latency, or it needs to work on the client devices, for example, and we cannot afford, building that on top of SQL, right? If you can go with Postgres, I would say go with Postgres as far as you can.
Okay, there is no best practices. You need to find your own way, as I understand. Okay, do you know Raft protocol?
Yeah.
Consensus algorithm?
And the Raft protocol basically follows the same rule I've mentioned about this two-phase commit. The difference is that Raft basically has a single leader, right? A single leader and multiple followers. This leader is chosen via another Raft-based election protocol because, well, it's part of the same protocol, but it's like it does two different things. One is leader election. So we need to choose who will be sending updates to all of the followers. And another one is this two-phase commit, which says that, okay, those entries were stored on the follower side. Majority of the followers agreed that this is the correct version of our replication log because Raft doesn't work. Well, it can work on top of key value entries, so records, but in the way that it's described and it works in most systems, usually and those are queuing systems like Kafka or RabbitMQ. It works on the append log fashion. So we are appending new entries to our log and committing them to the leader and to the followers once everything is done. So it's, again, consensus-based, and it follows all of the limitation of consensus-based protocols. So we have strong total order. So we know that all of the followers will eventually see events that we sent in the exact same order, right? But at least majority of the servers that are consisting to our cluster needs to be available. So, for example, if you have a single machine that got, network split from the rest of the cluster, you won't be able to send updates on that machine. So you will either need to find another machine, and if this is, for example, something that lives in your packet because this is the application on your phone that is using it, then you won't be able to send any updates because you will violate the consistency guarantees of Raft protocol.
Okay, thanks. Well, one more question about blockchain. Yeah, blockchain is a distributed technology. Yes, when we're speaking about distribution, eventual consistency, we can't not to talk about blockchain. Well, But the question is, are there any data types used in blockchain technology? And if yes, why was such choice?
Well, not in the sense of CRTs, because blockchain, as far as I remember, needs to be strongly consistent, right? Even more than the Raft, because Raft doesn't tolerate something we call Byzantine failures. So a situation when one of the followers, one of the nodes in our cluster might be malicious, might be hacked and have some malicious intent. In the case of blockchain-based protocols, they need to be able to work around that issue as well. And this is even harder level of consistency that we need to provide. And this is also the reason why so many blockchain implementations are so slow, because they need to be safe first. They need to guarantee that the order of our operations is strongly consistent, not like in the case of CRTs. So no, I don't think that you have any use case scenario for CRTs in sense of the blockchain itself.
Okay, folks. Thank you very much for Q&A session, and thank you, Bartosz, for your talk. Actually, I'm not working much with distributed systems as of now, but this kind of talks I really appreciate and really like. By the way, you mentioned Martin Klepman, who actually was at Hydra conference, which is about distributed programming and distributed systems, which will happen this year at this summer conferences as well. So this time he will talk about CRDTs. So if you are interested, please concern this fact. And we have a discussion zone which is available in Zoom meeting after the talk. Actually, in 20 seconds, you can go there and talk with Bartosz and Yuri. Thank you, folks, for this talk and discussion and Q&A session.